describing rotational motion. So it's going to be very useful in this unit to think about translational motion, which is what we did in all of the fall semester, things moving in a straight line, not rotating, and using analogies to get to rotational motion. So this is important because we're going to describe things differently because, as you saw in class today, not every point along a given radius is going to move at the same tangential speed. The farther out from the center of rotation it is, the faster it's actually going to make the same revolution in the same amount of time. So we have to use angles. Instead of describing things in terms of x and y, we're going to use angles. We're going to compare some translational and rotational motion quantities side by side. In translational motion, we describe position in terms of x and y. In terms of our equations, we just used x, because physics works in any coordinate system, but we just used x to make it easy. For rotational motion, we're going to describe position as angle, theta, which you've probably seen in math class to represent an angle. In translational motion, we had displacement, your change in position, final minus initial, and distance, your total path traveled. In rotational motion, you can also have displacement, final minus initial, or your actual distance that a point has traveled, in which case it's going to be that change times the radius. Now, if you're doing distance and you've gone around more than once, you're going to have to take multiples of 2 pi. In translational motion, we had velocity, which was your change in displacement over change in time, and speed, which was change in distance over time. In rotational motion, we have angular velocity, which is represented by the Greek letter omega, and so this is your change in angle over your change in time. Please remember that through this whole unit, we're doing our angles in radians. Here's where our analogy breaks. So when we talk about angular velocity, we mean omega. If I say speed and I'm talking about rotational motion, I'm actually talking about the tangential speed, which is actually omega times the radius. Angular velocity is sometimes also known as angular frequency or angular speed. We'll come back to that in a moment. For translational motion, acceleration is represented by a, and it's change in velocity over change in time. And in rotation, you have angular acceleration, which is represented by the Greek letter lowercase alpha. Looks like a little fish, which is change in omega over change in time. Okay, here's that warning again. In translational motion, velocity does not equal speed, but in rotation, angular velocity is the same thing as angular frequency, which is the same thing as angular speed. The word speed by itself, with no modifier in front of it, no angular speed, okay? If you just see that word, they're talking about the tangential speed, which is actually a translational quantity. I know, it's confusing. That's why this slide is here. So we have to talk a little bit about the mathematical conversion. So rotational quantities do not use the radius for the most part. So when we're converting, we want to take meters per second and make it meters per second with some radians thrown in there, and it doesn't seem to make sense. But if you look at a picture of a car tire going around, okay, the entire wheel is rotating at some rotational velocity, omega, all right, and a point on the outside of the tire has radius r, and so its velocity is going to be r times omega. The radians are in there, they don't cancel out, you're just going to have to kind of twist your head around it. So here's a table out of OpenStax with kind of a summary of how these work. The subscript down there on the A in the bottom right is a T for the tangential acceleration. For uniform circular motion only, I'll show you a derivation. So this is the tangential speed. You'll remember this from last week. So if I rewrite this as omega r instead of the tangential velocity, I can cancel out r's from both sides and rearrange. That one's on your equation sheet.